Hello everyone and welcome to Turbulence Modeling for Engineering Flows. So first of all, there is uh, uh, there is always asking about the modeling and modeling. What's the difference between modeling with one L and modeling with double L's? Actually, there is no difference whether you are modeling or modeling. You are doing the same thing. So the only difference is in the spelling. The one with the single L, when you write single L, is preferred in the United States, while the one with two L's is preferred everywhere else. So, for example, in Britain. Uh, Basically, this course has two parts. So one part is until the midterm, and the second part is after the midterm. The first part of this course includes more on physics and mathematics of turbulence, and the second part is more dedicated to simulation and modeling of turbulence. And if you want to simulate and model turbulence, you have to develop a solid understanding of its fundamentals and basics. And you need to know the concepts of nature of turbulent flows, the equations of motion, the statistical description of turbulent flows, because you have to learn to deal with random systems, not deterministic systems. And we will discuss that what kind of statistical analysis we need to use or to understand the physics of turbulence. Also, the scales of turbulent motion and spectral presentation, and um, we will finish the first part with a short introduction on modeling. In the second part, we will focus first on um, direct numerical simulations or DNS. And this DNS is basically solving Navier-Stokes equations without any assumption. So without any modeling, obviously, if your Reynolds number is low or you are in laminar flow, there is no problem to solve Navier-Stokes equations. If the flow is turbulent, meaning that more or less your Reynolds number is high, which we encounter in uh, engineering problems almost always, except for microsystems like micromechanical systems for drug injection and drug delivery, which are laminar flows. Other than that, in most of the applications in mechanical, aerospace, chemical engineering, all those involve high Reynolds numbers. So directly solving Navier-Stokes equations for high Reynolds number flows is not easy. Where where is the difficulty coming from? We will see that through this course. Obviously, it requires crazy amounts of computer resources. If you don't have this much of computational resources, then what you need to do is to model the turbulence. Modeling means you have a physical phenomenon, but you know that you cannot fully resolve this phenomenon because you cannot solve the whole set of equations. Then you say, okay, forget about the real phenomenon. I will use a model or set of equations so it will mimic the real phenomenon or it will mimic the turbulence. When you solve these equations, those model equations, everything will act as if there is turbulence generation, turbulence dissipation. And this set of model equations will hopefully accurately mimic the real case. And for the past 120 years, people have trying to do this modeling. And This involves the eddy viscosity models and Reynolds stress and related models, and also partly large eddy simulations. So, after having a look at the course outline, which is a very extensive course actually for you, let's see the references that we have. So, these are the references, actually, four references. And by the way, these are not your textbooks. So, you shouldn't follow any of them word by word. I'm not following it word by word, but these are very useful for you. The first one is The Turbulent Flows by Stephen Pope, and we commonly know this reference as a Bible of turbulence. It's very difficult to understand, but it contains all relevant mathematics and physics for the turbulence. The turbulence itself is all about mathematics and physics. Of course, we apply it in engineering because we have to solve different problems, but you are expected to develop a solid understanding of mathematics and physics, like tensor mathematics or vector mathematics. We will review it shortly, and also the physics, fundamental flow fields. The second book is also fundamental, a first course in turbulence. It's a very old book, 1972, but it never gets old. As fluid mechanics expert, you should have this book in your library. The third book is the Fluid Mechanics, and it is in graduate level, not in undergrad level. It has very good introductory chapters related to turbulence. Not the whole book is dedicated to turbulence, but it's very useful, and we also review some materials from that book. And the last book is from Wilcox. I suggest you to actually obtain all of these references and put it in your library. Turbulence modeling for engineering flows. This is the title of the course. And you know what these pictures are, right? These are Leonardo da Vinci's pictures, drawings. What does Da Vinci have to do with turbulence, you may ask? Da Vinci was a great observer. Also, you have to be a great observer since you are doing your master's and you are in the footsteps of Da Vinci to become very successful scientist. So you have to become a very, very good observer of nature. What do you see in these pictures? For example, in here, in here, what do you see in here in these pictures? What do you see in here? So he put a plate, or there was a plate inside the water. One plate was kind of aligned with the water stream. One plate was normal, and he was seeing different patterns that were shaped inside the water. Or for example, in here, or either in here, and then there is a channel that the water drops from this channel inside one tank, and he was sketching it. So all of these pictures that you are seeing, uh, actually these are not very, very randomly drawn lines, and we will discuss about all of these uh, later. Okay, let's start from very, very basic. Uh, Just a second. So this picture is, you know, uh, when we talk about matter in general, it could be in three phases. That's what you actually know back in your elementary school, or let's say middle school. Solids, which hold the shape, and that's the definition of solid. In reality, there is no difference between solid and fluid actually. So we do have stresses in fluids as well as a strain, principal axis, we have all of those. And the only thing that creates the difference between a solid and a fluid is that the fluid cannot hold their shape, but the solid can. A fluid can be liquid or gas. We know it. Both of them takes the shape of their container, and in a liquid there is always a free surface, so it's boundary between liquid phase and gas phase, and the gases completely fill the volume of their container. So this is what we know about the matter right now. Now, in physics, what we want to do is actually to understand, in engineering especially, the motion of fluids. Motion of solids is what we call dynamics. So, dynamics people have their own community, but motion of fluids is what we are interested. For solids, it's been described before. How to define the motion of a solid, we know it. It depends on the equation, summation of forces equals to mass times acceleration. So if you have a solid body and you have a lot of forces acting on it, if you sum them up and end up with a net force on the body. So this is the net external or net force. Uh, that force of that body, and when I say body, I'm assuming it as a certain mass, and that net force is critical here, and that's why we have sigma sign. That net force causes this body to move or to accelerate in, let's say, some direction. So we've known all these since Newton. The question is, okay, F equals ma, but what is a? What is acceleration? Instead of writing like F equals ma, we can write it as F is equal to m dv over dt. Okay, acceleration is the time derivative of velocity. Okay, so why is it important? What can I do in one further step? As you see in here, if mass is constant, just consider that you have a solid object, it is moving around, it is accelerating, decelerating, but its mass is not changing, it's constant. If that is the case, I can take mass into the derivative. So I will take this mass inside the derivative. So it's actually a time derivative, ddt, time derivative of what we call as momentum, m mass times velocity. The physical concept of momentum is this. If there is a net force, there is a net force applied on a solid object, changes its momentum. So the time rate of change of momentum. This is actually what equations tell me. How do we actually perceive? How do we understand this momentum change? There is a solid interaction. You can see how things get deformed. You can see two solids exchanging their momentum. Again, let me check if it is recording in here. The thing is, if the speed is high enough, for example, this is a golf ball impacting at a very high speed, uh, kind of uh, like 150 miles per hour. It is impacting on a solid steel surface. So this is a very stainless steel surface. As you see, the golf ball acts like a bubble. See, this is a golf ball. It's a very solid thing, but it is acting like a bubble, or what we call as a Brownian motion. So it is Brownian motion. It's strange, no? If you're not getting angry with me, I have to say that solids also are subsets of fluids. Now, what we want to do, if we have a solid sphere ball, if it has a net force acting on it, it will travel from some place to another place, and in fact, its linear momentum is changing. The problem is if this sphere has flexible boundaries. Okay, this ball has a flexible boundaries. Flexible meaning that the boundary is also changing with time. The question is this: the boundary is also subjected to F equal ma, right? F is equal to ma, but the boundaries of something also are subjected to this. The question is, how do we apply the same equation to this geometry? Okay, the same equation, how do we apply it? What Newton says, it says that it has to obey governing equations of linear momentum change. But the boundaries are now flexible. So at some time the boundary is like this, at another time the boundary will be like this. So the boundaries are flexible. Initially, it was very, for example, straightforward in terms of a golf ball. It was like this. It was a golf ball, and then two solid objects colliding. It collides to this stainless steel, and then after some time, it was like this. The ball was like this. You could calculate the momentum transfer, and you may have done this in the basic physics classes. The problem in fluids is that our boundaries are changing in time. Okay? The boundaries are changing in time. And this change in time could be random. It may not be deterministic. How do I apply the same governing equation to a system in which boundaries are changing? How do I do this? Okay, fortunately, you don't have to find that answer because uh, Leibniz, Leibniz, he was a mathematician. He found that answer for you. So, what's the, for example, there is a, let's say, distribution of some function f, and you see this distribution of function f that is changing in space and in time. So at some point, the boundaries of f are at point A and point B. Okay, and after a while, you see that the distribution of F is changed. So its boundaries also changed, and the boundary at A moved to this point, and boundary at B moved to this point. So at some time t plus delta t. So the question is how to interpret it in the form of, let's say, mathematics. So mathematics says that the time rate of change of this function that is limited within two boundaries, that these boundaries are function of time, boundaries A and B function of time, you have to calculate it like this. So first of all, you have to consider the change of the function through time, and also you have to consider the change of boundaries through time. So if you want to do an integration of a system which has time varying boundaries, as in here, this system has time varying boundaries, you may use this Leibniz integral rule. What you need to do is to first find the time variation of the system inside. So this is the time variation of the system inside. And then find the time variation of the boundaries. This part, this second part. If they are expanding or moving back. Like what we are showing in here, boundaries are moving. A moved to this point, B moved to this point. So it could be expanding or it could be moving back. So what is if you want to write this, change from A to B is actually, this is the same thing as you have in the upper formula. So this is the Leibniz integral rule. And this is just a pure mathematics. You see just two formulas, it's pure mathematics, and it is applied to physics laws. So let's see this Leibniz integral rule in fluid mechanics. If you apply Leibniz integral rule for boundaries changing like for the fluid particles, then the name of this Leibniz integral rule will be changed. We call it Reynolds transport theorem. So this is actually the same thing. This equation is the same as Leibniz integral. You have a system, yeah, in here you have a system. You want to integrate it over time. So if you want to see how the system changed over time, the boundaries are also time dependent. If the boundaries of this system are also time dependent, you see similar terms. You see what is changing inside the control volume. We have a volume. It's not two-dimensional, it's three-dimensional. It is in general three-dimensional. And also you have to take into account the variation of the surface in here. So in a better way, if you write it, it's a function f that is its boundaries are changing with time. So the time rate of change of such system is actually equal to time rate of change of the control volume plus the variation of actually the fluxes on the control surfaces of this control volume. So we know it as um, Reynolds transport theorem. So if you use this, you can actually apply uh, what you had F equals to ma to fluid system. So it is a system of fluid. And when you apply this, you get nothing but the momentum equations or Navier-Stokes equations. So you just apply F equals ma to uh, Reynolds, let's say, transport theorem. So instead of this function in here will be your momentum, or the b function in here is your momentum, and this b is your moment is the momentum per unit density. So if you apply it, you will end up with actually Navier-Stokes equations, which are the momentum equations. And actually, the Navier-Stokes equations, if you look at it, it's actually F equals ma written in the opposite form. So this is actually ma part, and this is the forces, or let's say sigma of the forces, net forces. What are these forces? You see some pressure forces, and you see some viscous forces, and you see gravitational force in here. So everything on the right hand side is actually actual forcing on the fluid particles. Like uh, I'm forcing you to read these papers that I want to assign. These are the forces that are applied. How can you force the fluid? We said pressure difference, friction, and also body forces like gravity, electromagnetic force, and etc. And if you force the fluid particle, Newton says that its momentum should change. This is how we describe fluid motion. You know that Navier-Stokes is actually uh, you have the continuity plus momentum equations that will shape the Navier-Stokes equations to you. So in this class, you will get exposed to lots of uh, I'm showing to you lots of I's, lots of J's, and it's called indicial notation. It's very critical in terms of tensor mathematics. And if you see Navier-Stokes equations in here, um, I have three equations for, let's say, momentum, and it takes a lot of space to write. So we just write one equation with indicial notation, which represents the whole equation. So for the continuity, for example, I'm writing dui dxi equal to 0, and you may ask why you are writing just one term, because in continuity you have three terms. So when we use indicial notation, when we have repeated indices like dui, dxi, I and I are repeated, it means that you have to do the summation over this. So we will talk about this, but uh, you have to know all of these when we want to proceed. And you see that instead of three equations in here, I just wrote this equation rho and times dui dt plus uj dui dxj. So you see again in here you have a repeating index. It means that it has to be summed up over j. J is equal to j is equal to 1, 2, and 3. So for example, j equal to 1 will give you this x component, the whole equation, x component of the Navier-Stokes. J equals to 2 It will give you the y component, and j equals to 3. It will give you the z component of the Navier-Stokes equations. The problem is all the fluid flows, whether they are extremely low Reynolds number or let's say creeping flows, and it goes to hypersonic flows. All these flows are governed with these equations, with uh, Navier-Stokes equations. There is only one condition, and it has to be continuous, or it is continuum. Everything has to be continuous. If you have discrete fluid particles, for example, one particle is here, another particle is 2 meters away, and they are not connected to each other, you cannot apply these equations. You cannot apply, let's say, Navier-Stokes equations. How do we determine if a system is continuum system or is a discrete system? You know that we have a non-dimensional number known as Knudsen number, Kn, Knudsen number, and we thought you many years ago in fluid mechanics classes, depending on the value of Knudsen number, you can determine if a system can be thought as a continuous system or a discrete system. If it is continuous, you can use Navier-Stokes equations. So you know this Knudsen number is actually your mean free path over your length scale. And if this value is smaller than 0.01, you are having a continuous system.